All right, 2016 AIME 1, question 10. A strictly increasing sequence of positive integers a1, a2, a3, all the way to a9, all the way up to a13, mixing up my problems now, has the property that for every positive integer k, the subsequence a to 2k minus 1, 2k, 2k plus 1 is geometric, and the sequence 2k, 2k plus 1, 2k plus 2 is arithmetic. Suppose that a sub 13 is 2016. Okay, let me show you just an example of what's going on, then we'll dive into the problem, because in order to make this video not be 40 minutes long, I'm going to have to move along here. So first thing we need to understand is this. I'll do a little bit of an example. If I start, let's say, at 1, from term 1 to 3, this has to form a geometric sequence. So let's just say I'm going to use the geometric sequence multiplying by 2. It has to be strictly increasing, so it would be 1, 2, 4. But this needs to form a arithmetic sequence, so this term here now has to be 2, 4, 6. Okay, because now they are adding up by 2. But now this needs to form a geometric sequence. So to get from 4 to 6, we multiply by 3 halves. If we multiply by 3 halves again, we get 9. And so forth and so on. I'll put a couple more up here. So now I need another arithmetic sequence. So 6, 9, I'm adding on 3, 12. And to get from 9 to 12, I multiply by 4/3. So the next one that I get, 12 divided by 3 is 4, times 4 is 16. And so forth and so on. But the pattern that we need to catch is this. So if I'm multiplying by 2 over 1 and 2 over 1 for the first pair, I jump into another arithmetic sequence or geometric sequence, and I'll multiply it by 3 over 2, and then 3 over 2. And then I'll multiply by 4 over 3, and 4 over 3. And you could probably guess now, next one's going to be 5 over 4 and 5 over 4. And so I can actually get a lot of information without having to find all these terms. That's going to help us. All right, let's clear out this mess. And get back. Actually, let me just do it this way. Get back to a fresh, clean slate. Okay. Ooh, almost. All right. So now the problem at hand. I need 13 things. So a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. In this 13 spot, I have 2016 sitting here. I need to figure out how to get there. Well, I don't know what to start with yet. That's what I need to find. But I'm going to start here and work backwards. And so in here, label this is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And the geometric sequences have to go 11, 12, 13, because it's odd, even, odd. 9, 10, 11. 7, 8, 9. 5, 6, 7. 3, 4, 5. And 1, 2, 3. And then the purpose, the importance of this arithmetic sequence is that it causes that pattern where we saw that the numerator and denominator were both increasing by 1 to get from each geometric sequence to the next. Next thing, and I told you in an earlier video, it's super useful to know the prime factorization of the year. They throw those in there on a ton of AMC and AIME questions. I need it again. The reason I need it is I need to figure out how I can make a geometric sequence that will to go backwards. So I'll factor down 2016. Now I did this before, so I know 16 goes into here 126 times. You could bring out a bunch of 2's. You have some time for this, so 16 is 4 times 4. I could even jump to 2 to the 4th here, so I'll write that here. 126, well, we get a 2. 2 times 63. 63 is 3 times 21. 21 is 3 times 7. So I end up with 2 to the 5th times 3 squared times 7. And I want to have the smallest positive greater than 1 common ratio I can get. So what I can do is if I'm working backwards, so if I'm going backwards, I can multiply this by something. I have to do it twice because of the geometric sequence. And so in here, I have enough 2's to divide by 2 squared, and enough 3's to divide by a3 because I need to do it twice. And 2 squared times 3 is, of course, 12, so let me replace those with 12's. So put 12's here. And I want to get this to be as close to 1 as possible, so I'll multiply by 11/12. Now, if I'm going backwards and getting 11/12, then going forwards gives me times 12 over 11. And now I can just follow the pattern I saw before when I showed that sort of smaller case. It can sometimes be very helpful to look at a smaller case you can really wrap your mind around before you jump into this case, because if you do a large case like this and you do something wrong, you gotta start all over. You don't have that much time. So this was 12 over 11 times 12 over 11. Working backwards, this is going to be 11 over 10 and 11 over 10. And I keep on going. 10 over 9, 10 over 9, 9 over 8, 9 over 8, 8 over 7, 8 over 7, 7 over 6, 7 over 6. And when I take my term 1 and multiply by all this stuff, I get 2016. So term 1 times, so I have, I'll just put a big old fraction here, so I have 7 over 6 times 7 over 6 times 8 over 7. And I think you can probably see where we're going with this. 8 over 7 times 9 over 8 times 9 over 8 times 10 over 9 times 10 over 9 times 11 over 10 times 11 over 10 times 12 over 11 times 12 over 11. And that's equal to 2016. And the 7's, the 8's, the 9's, the 10's, the 11's all cancel. I'm left with 12 times 12 over 6 times 6. Well, 12 over 6 is 2. So this is really 2 times 2, which is 4. So I end up with A1 times 4 equals 2016. And just divide both sides by 4. So 2016 divided by 4 gives me 500. Ooh, that's not a 5. 504. Okay, comment with any questions, and I'll get back to some of these maybe tomorrow or the next day.